Our next talk is by Samuel Hutchinson, and his topic is classifying online misinformation and cognitively informed features from transformer language models. Sam?
Okay. Yeah, so as Professor Ramez just talked about, my title is Classifying Online Misinformation with Cognitively Informed Features from Transformer Language Models, and we will get into what all of these big words mean in a little bit. But first, I want to thank my advisor, Dr. Christopher Baldessano, for helping me get this project. And yeah, so let's get into it. So a little bit of background. Anyone who has been existing in our sort of media landscape for the past few years is obviously aware that misinformation is playing sort of a larger and larger role in what we're talking about and what we're reading and what we're seeing. And so I felt it would be sort of interesting and important to look at what gives misinformation sort of its cognitive potency. People have found that it is, for example, 70% more likely to be retweeted than true information if a tweet contains misinformation. What exactly is driving this? So two ideas that I had coming out of the cognitive science literature were that it's sort of the emotional valence and the informational novelty. So the information is both surprising and sort of upsetting. And this sort of drives the increased engagement with it. So then stepping forward into a more practical question, I wanted to know, sort of bringing in sort of my computer science background, are these two features not only particularly salient in misinformation, but are they computationally modelable? And so, yeah, so this project was an endeavor to see if such a thing could be done. And a bit of a preview, yes, it can, with around 80% accuracy in classifying unseen news stories. So, yeah, we'll get into what exactly this entails. So, sort of stepping through this a little bit more slowly, my research problems were sort of threefold in looking at three sort of outstanding questions in the literature. So the first question, what distinguishes misinformation? I'm, for the rest of the talk, going to be referring to it by fake news, which is sort of the phrase used in the literature, from non-misinformation, which is like regular news, to human readers. Secondly, to what extent do misinformation detecting machine learning algorithms use cognitively interpretable features, in that there already are algorithms that can classify misinformation with accuracy rates upwards of 90%, but as we'll get into in a little bit, they have sort of some issues with interpretability. And then sort of the big theoretical question, to what extent do human readers and language models overlap in the kinds of computations that are happening as they're processing natural language? So, trying to answer the first question, a common way that people investigate the way misinformation varies from true news stories is by looking at people's reactions to it. So is there a significant difference in the way people sort of subjectively respond to these two types of news information? And people find that surprise and disgust are the two emotions that are sort of overwhelmingly associated with fake news. And we can see this here. So on the x-axis here, we have the percent of users who responded to the news story with a particular emotion, and on the y-axis, we have the particular emotion that is being responded with. The red bars represent the responses to misinformation, and the green bars to true information. And pointing out, again, these two things, we see this significant difference here in disgust and in surprise, with misinformation having elevated rates of both. So then moving on to the second question, how do machine learning algorithms classify misinformation? And in short, they do it very well, sort of like I mentioned, with very high accuracy rates. But they're black boxes with parameters occasionally numbering in the billions. And so looking at when it's making a particular classification, noting that a couple of the parameters seem different than usual, that doesn't really tell you much about what features of the news story are tipping off the algorithm to these kinds of classifications. So, and there's been sort of a bunch of research recently on this. And then moving forward into my sort of biggest question, how are humans and language models similar in their linguistic processing? Two sort of features that the research keeps landing on are in that humans and language models find similar word context pairs surprising or predictable. And so there's been sort of a flurry of recent research on this in the past couple of years. Here are some figures I found particularly helpful. This is from the first of these studies, the Goldstein et al. So on the farthest left, we can see on the x-axis sort of the proportion of people that got the word correctly in a next word guessing task. And so given a sentence like, I'm very thirsty, so I'm looking for a water blank, if the correct answer is bottle, the x-axis shows the number of people in the study that actually correctly guessed the word bottle, and the y-axis is the number of times that a GPT-2 language model correctly guessed the word bottle. And so given each of these data points, which is a different sort of word context pair, we can see that there is a pretty strong correlation between the kinds of word context pairs that humans find easy to guess and what language models also find easy to guess. So here's sort of an interesting behavioral comparison. It's then moving even deeper into maybe some neural similarities. We can see in that middle graph, the x-axis is the time after the onset of a word. So as you're listening to me speak, if I say the word cat, it's been about 1,000 milliseconds. And you can see on the x-axis, this shows the time after the word onset, and on the y-axis is the electrical potential as measured from people's scalps. And you can see that there is a peak for incorrect predictions, words, these pairs that were less predictable, at around 400 milliseconds. And those of you who are more familiar with sort of traditional ERP linguistic work, the N400 is traditionally associated with sort of a semantic error in a sentence. So I say like the cats are baking, about 400 milliseconds after you heard me say baking, your brain did that. So because that was sort of semantically unpredictable. And so how does this compare to what's going on in a language model? The graph farthest to the right, the purple line in particular, is looking at this particular measure from the language model called cross entropy. And the y-axis shows the correlation of this measure with the human neural response. And you can see the correlation peaks at around 400 milliseconds, indicating that there's perhaps some similarity, at least in timing or the kinds of computations and how that's lining up with the timing of human neural processes, of sort of difficult predictions with elevated rates of language model cross entropy. So this is sort of the key human neural factor that motivated my study. So how does my project come into this? So given that what we just saw, that humans and language models find similar word context pairs as surprising, and that humans find misinformation surprising, my hypothesis then is that this prediction error cross-entropy measure from language models can be used as a proxy for human surprise in a classification of misinformation. So what this sort of provides to the literature is a new context for comparing humans and models, which is sort of, as evidenced by all the studies in the previous slide, sort of a big topic right now. It shows maybe a sort of a peek inside these black box models, as maybe these are some features that some combination of the parameters are picking out. And also this gives a better understanding in general of misinformation and its sort of computational qualities. So how exactly did I go about trying to answer these questions? I use this big data set from the Information Security and Object Technology Lab at the University of Victoria. It has about 45,000 news stories. A little more than half of these are fake news stories. A little under half are true news stories. All the true stories are sourced from Reuters. All the fake news stories are sourced from stories that have been labeled untrustworthy by PolitiFact. So the data set is entirely human labeled, which makes it pretty easy to work with. Divide this large data set into training and testing partitions. And then for each story in the training partition, go over and build a data set compiling both the average prediction error and the sentiment for each of these stories. Plot these two different measures by news type. And I know this is maybe a little bit unclear right now, but we'll get into what exactly this density plot looks like in a second. Use these distributions then to predict the label of an unseen news story, and then repeat for 3 cross-validations to make sure any results we might have gotten were not just a feature of the particular sample of the data set that I took. So what do I mean by classification? Really, sort of this is exactly what is going on. We can see these two sort of proportionality statements. On the far left-hand side, you have the probability of a news story being false on the top row, probability of a news story being true on the bottom row. Given the 2 pieces of evidence that I'm extracting, the sentiment, so S, and the average cross entropy, the CE measure. And so in sort of typical Bayes fashion, we can calculate these, or at least sort of configure that they're proportional to the probability of getting a certain value of the sentiment and a certain value of cross entropy, given you know what type of news story it is, multiplied by the rate at which that type of news story appears. So how does this actually play out? So here are the results. And on the x-axis, here I'll explain the y-axis first. The y-axis, we have this measure of surprise or predictability. So towards the top is more surprising, towards the bottom is less surprising. And on the x-axis, we have sentiment score. So -1 is the most negative, compared to +1 is the most positive. And we see that here that we have two sort of distinct clusters. And the filled-in cluster represents the fake news stories. So we can see they're more negative and more surprising in general, compared to the true news stories, which are comprising the empty cluster, which are more neutral both in tone and sort of surprise. And the key fact to notice about this graph is sort of this clear separability of the maximum density regions here, right? And so to illustrate this a little bit better, I have a different view of this graph. So if you notice sort of the numbers around the rings are increasing as they go up. This is sort of the density of the data within that region. So if we take these numbers and instead sort of pull them up along the z-axis, we get a graph that looks like this. And so you can see more clearly here sort of how separable these two distributions are. So this will be what sort of facilitates the predictions that I'm about to show. Yeah, so that's sort of how it shakes out. And so then for testing sort of what I was talking about using these distributions to predict, imagine you were given a new news story, and you can calculate its sentiment score, and you can calculate its average prediction error, and then you sort of just plonk it down on the graph somewhere and see what density region is it in. So if it's in that sort of really dark red region, you know that there are a lot of fake news stories also clustering around there, so you can make this prediction that perhaps this is more likely fake news. So how does this prediction actually work? It works pretty well. So first measure to draw your attention to is sort of this overall average accuracy of nearly 80%. And you can see sort of on the unbolded columns in that top chart, the various values for the different cross-validations. The accuracy for each cross-validation was significantly greater than chance. Chance for the testing data set was about 2/3, given that about 2/3 of the story were fake. And so if you just guessed fake every time, you get 2/3 right. But the p-value for the permutation test for all three of these was less than 0.01, indicating some robustness to the classification actually being above chance levels. But then a second measure that I want to draw your attention to here is sort of the elevated false positive rate. And that ideally this would be something that we would like to see a little bit lower. Nearly 42% of the stories that were actually true were predicted to be false. And I think there are a couple of reasons why this might be. One could be that some news stories are, just by their very nature, both surprising and negative, like a bank collapse, for example, would register as both something that is sort of semantically unpredictable and also negative, and therefore more likely to be classified as potentially containing misinformation. Or this is just a feature of what makes news stories compelling, in that if these two factors drive misinformation to be sort of increased in its viral sharing, it could be that true news stories are also sort of writing in such a way to garner the similar kinds of attention, which would then lead to, I think, them exhibiting sort of the phenotypic traits that I'm associating with fake news here. So how generalizable are these results? This is data from a different data set, which instead of using sort of a binary classification of true or false, instead has a more graded system, so 0 being the most false, 5 being the most true. And so these are looking at sort of the two measures that I was looking at previously. So the graph on the left, we have sort of this veracity category versus sentiment score, and we see that the trend is in the same direction, in that as news stories are getting more and more true, their sentiment is approaching neutral, right? It's going from sort of a mean of about -0.25 closer to 0, positive rank correlation there. And on the right, we have a decreasing prediction error as the news stories become more true. So again, in the same direction, but very slight effect. So what are some takeaways here? So there seems to be evidence in favor of my initial computational hypotheses that surprise and sentiment are both computable and make for sort of interpretable classification metrics. And then breaking down what exactly is going on with this language model surprise is a little bit more of a difficult question to answer. It could be that one thing driving the sort of incorrect predictions, the higher prediction rates, is some sort of syntactic malformation. You can imagine that true news stories go through a more rigorous process of spell checking and so on, right, or grammar checking. And so misinformation news stories may contain simply grammatical mistakes, which a language model will find sort of unpredictable. Or there could be sort of this genuine semantic unpredictability, like I was talking earlier. So for example, in the context of like a news story, Hillary Clinton is A. If the next word pops up as criminal, that was likely not a predicted word in the new language model hierarchy. Therefore, this could likely be sort of classified as misinformation because it's sort of this semantic unpredictability, even though it's sort of grammatically well-formed. And then in terms of human surprise, how does this compare? This could draw from two sources. One is sort of a logical conflict, and that if you look outside and I say, oh, the weather today is sunny and warm, you might think, well, that's like totally in conflict with what I know about the world, and so then I'm sort of surprised that you said that because I wasn't expecting you to stand up here in front of a podium and lie to me. Or it could be drawing from a more fine-grained semantic unpredictability again, in that looking at that sentence maybe a little bit more closely, I say the weather outside today is, you might expect me to say something like cold or rainy or cloudy. And so then when I say warm, maybe this is where sort of the surprise is generated, not in sort of the integration of the whole thing, but in sort of this particular unpredictability. These two possibilities are not exactly mutually exclusive in that, like, again, sort of like this logical conflict surprise could be underlyingly drawing from the semantic unpredictability. So the question then is, are these the same kinds of computations? Are these the same kinds of surprise? And I think this experiment provides evidence sort of in favor of the idea that next word prediction does play sort of a fundamental role in driving human response to language. Sort of in line with sort of those ERP graphs I was showing earlier, that this shows that sort of the same things humans find surprising, language models find surprising, and maybe for the same reason. And so, yeah, so in short, misinformation is significantly more surprising and significantly more negative. These things do seem to be computationally tractable and interpretable. And this is further evidence, again, in favor of this similarity between humans and language models. So again, thank you to the Dynamic Perception and Memory Lab, Dr. Chris Baldessano, and the Columbia Cognitive Science Program.
Sam, we have a room full of people who share fake news fluently, who want to ask a question about this. Who's first?
Hi, Sam. That was terrific. The large language models are trained on basically everything out there, and probably the amount of fake news out there, I hope, is relatively small. Then the data set that you're using to test your hypothesis is one in which, if I remember correctly, half of the news headlines are fake news. And I'm wondering if maybe that could explain, because it's looking for things that are unlike what it's been trained on, and that's why it finds it surprising. But then I was wondering whether this result would really generalize to the news environments we regularly live in, which might include, for some people, much more fake news, and so it wouldn't be so surprising. Do you know what I mean? So maybe the effect is just the different ways in which the training data for the large language model and then the data set that you're testing it on.
Yeah, I think it's definitely true. One sort of more nuanced detail that I didn't go into in the presentation, but I can sort of pull up here, is that you can see a model that is fine-tuned on true news stories. So the graph on the left, the sort of plots on the right, shows a greater difference. Shows a greater difference in cross-entropy than one that hasn't been fine-tuned. So that's sort of, again, in favor of what you're saying, that it's sort of the prevalence of the two types of the data set that is looking for things that are different. And yeah, I think people certainly who live in a media environment more saturated with fake news would find it less surprising. But then I would wonder what drives their continued engagement with it. If sort of the idea is what drives the initial engagement is this sort of like, oh, this is a crazy fact that I don't know. If you're constantly inundated with misinformation, I wonder, as far as I know, there haven't been any studies that I've seen that show like rate of misinformation engagement compared to misinformation saturation. But that would be an interesting thing to look at.
Another question. Sam, thank you. Oh, sorry?
Hi, I just wanted to ask sort of what would you have to study on the last graph or the last slide when you were showing your takeaways? What would you have to sort of tease out to know if the LLM surprise is syntactic malformation versus semantic unpredictability? Like what kind of more information would you need to know?
So we can look at sort of what things the model identified as being sort of surprising. So here are some examples. The bolded words are the ones where the sort of prediction error peaks in the news story. And so like if you consider like lol to be sort of a syntactic malformation, which I think in like a language model's predictability it might be, then there's sort of examples like that. But a lot of the ones that sort of come, this is just sort of a random sample taken, are sort of syntactically well-formed. The Donald listening, State Department misplaced, did Hillary die? These are all sort of syntactically well-formed, but semantically unpredictable. Yeah, so I think in this data set in particular, there's good evidence to think that it was semantic unpredictability. So.
Thank you.
If you wanted to enter the competition to knock off a portion of the 20% that the model misses, would you introduce a new encoding parameter? Beyond surprise and disgust.
Yes, I think so. I think this is sort of a complicated question given this data set, because I think a limitation of this data set is that all the true news stories are from Reuters, which gives it sort of this sense of like, there's a formality component which distinguishes them, which I think sort of these things like lol, which are like maybe not quite syntactic but not quite semantic, sort of a stylistic component. So
This is linguistic formality.
yeah, yeah. So I think something along those lines. But if that's just maybe confounding what I know of my data set with how I know the results came out, but you know.
You have to solve the descriptive problem of how to characterize formality.
Yeah,
Right.
Yeah, that's true.
Which would be fantastic if you could do that. Thank you, Sam.
Thank you.